OK, let's look at the issue logic here and a pipeline diagram. So here we have op A, B, C, D, E, F. So we have straight line code, no branches. And we have things flowing down the pipe, and we have our nice pipeline diagram. And one of the cool things is now that we have a 2-wide superscalar, we can actually violate a rule that we had before, which said two things cannot be in the same pipe stage at the same time, temporally, because time runs from left to right on this diagram. So here we have two things in the decode stage, two operands, or two operations, or two instructions in the fetch stage. And we're just going to name, because we don't have a great name for these things, we're going to call these A0 and A1 and B0 and B1 to represent the different execution unit stages. So in an ideal world, this is pretty sweet. At least for this code here, we actually have a clocks per instruction of 1/2. That's pretty awesome. And as I said, we can have two instructions in the same stage of the pipe. OK, let's look at a little bit more complex code sequence here. We have add, loads, some more loads, an add, a load. Your issue logic, that swapping logic, actually will have to move instructions around in this case. So we have this add and this load. Well, this is actually easy. The add goes to the A unit. The load goes to the B unit. No problems there. OK, so now we have the load. Uh-oh, load's in. We fetched it, and it's in the instruction register 0. That means it wants to go to the A pipe. But we need to swap these two. So you can see here, this is how we draw this. We actually say this add is going to the A pipe here, and that's the opposite of what's going on there. But there's still no stalls going on, at least in this example. And then finally here, we actually are going to get a structural hazard. And the structural hazard introduces a stall. So we fetch these two loads simultaneously, but we can only execute one load at a time. So we need to stall one of the loads in the decode stage and push that out a little bit. So it actually has a different pipeline diagram than the no stall, or the no conflict, no structural hazard example. OK, so let's look at a little bit more complex example here, a dual issue data hazard. What happens when you have data hazards? So unfortunately, when you have data hazards, you can actually, so this is without any bypassing. This first example, this first two instructions here don't have any data hazards. But here we have a write to register 5 and a read from register 5. And this is a read after write hazard. And because we're not bypassing in this pipeline yet, we actually have to stall the second instruction waiting for that first one, even though we could have potentially executed them at the same time. But there's a real data hazard there. So we need to introduce stall cycles into the second instruction. Does this make sense to everybody? So we're going to push out that add. If we have full bypassing, we still need to add stalling, potentially. So now we don't have to wait for this value to get to the end of the pipe to go pick it up in the ALU. But we can pull it back because we can bypass, let's say, the add result after A0. And what you see here is the same instruction sequence. But now it's bypassed from A0 into the decode stage, and we can start going again quicker. So bypassing is really helping us here, and it's crossed with the superscalarness, if you will. So what I mean by order matters is that here we've interchanged these last two instructions. So we just flipped them, and we turned what was a read after write hazard into a write after read hazard. And because of that, this actually pulls in by one cycle, and we don't get the stall. So just by changing the ordering of the instructions, it'll change the data dependencies. And that will actually change the ordering and change the execution length. Does that make sense to everybody? Why we can actually interchange two instructions and the data dependencies completely change, and we need to worry very different things about the data hazards. OK, so I want to briefly wrap up about fetch logic and alignment. So this is, someone was alluding to, I think you were alluding to this. let's look at some code here that's going to take jumps. So execute some instructions. So this is the address. This is the instruction. And we have a jump here to address 100 hexadecimal. And then we execute one instruction opd, and we jump to 204 hexadecimal. And then we execute one instruction and jump to 30C hexadecimal, and then we just execute some stuff. Here is our cache, and let's say our cache, the block size is 4 instructions long. And we're going to look at how many cycles this takes to execute. So let's say there's no alignment constraints in the first case. So in cycle 0 here, we execute these 2 instructions, and we fetch them from the instruction cache, and they're aligned nicely together. There's nothing sort of weird going on. We just go pull them out. OK, these next 2 instructions, 8 and C, those are next to each other. That's great. And then we jump somewhere else to 100, and we're going to execute these 2 instructions. They're next to each other. And they're at the beginning, and they're aligned. So that's great. No problem there. OK, now we start to get some weird stuff. Now we jump to sort of the middle of a cache line. In this example here, we jumped to some address 204. So our block size is, as I said, 4 instructions. But we're sort of jumping not to the first instruction in that block. So in a fully fleshed out fetch unit, let's say you can execute with any alignments. So life is easy. We can just fetch, and we can execute these 2 instructions at the same time in the same cycle. In cycle 3, we fetch both of those. That could get harder if we actually try to put some realistic constraints in that. OK, now let's jump to the end of a cache block. And we're going to try to fetch these 2 instructions at the same time. So one is on this cache line, and one is on that cache line. Do we need to fetch 2 things from our cache at the same time? Yeah, we do. If we actually want to try to execute this instruction and that instruction at the same time. Let's say for right now, this issue logic actually allows us to do that. Somehow it's a dual-ported instruction cache, we'll say. And then finally, op5 here, or 314 executes last, and it's just sort of fall through, and there's no jumps or anything happening. So some things that can be really hard to actually make work out right are fetching across cache lines, and possibly even fetching randomly inside of a cache line, depending on your fetch unit logic. And like I said, we might need extra ports on the cache. Here's this code executing. And as you can see, we don't actually get any introduced stalls. It just sort of executes this, then this, then this, and you can execute 2 instructions every single cycle. Now let's look at some alignment constraints. So here's our original example, and let's look at what we could possibly try to execute here. So we're jumping. If you recall, we only use these 2 instructions from the middle of the line. So let's say we can only fetch a half a block at a time or something like that in each cycle, because that's just how wide our cache is. So what you might have to do in some architectures, if you have alignment issues like that, and let's say you're not allowed to ever straddle, you'd actually have sort of extra data fetched that you're just never going to use. So you're just throwing away this bandwidth. And also the cycles of this change. So let's look at this same code sequence and look at what happens when we go to execute it. So going back to this. So we execute op A and op B. OK, those just go down the pipe. Life is good. We get to this address 8 here, 8 hexadecimal. Well, we need to swap that because the jump needs to go down pipe A. But otherwise, things are OK. Well, now we jump to the middle of a line here. That starts to get more interesting. And we're going to basically end up wasting cycles So this will take 7 cycles, where before we had this taking only 5 cycles, because we've effectively introduced dead cycles where we fetched instructions we just didn't use. So the 3 X's here show up as instructions we fetched. So like, for instance, this instruction, or the instruction at address 200 is that. We fetched it, and we're not using it. And we fetched these 2, and we weren't using either of them. So having a complex fetch unit or a not fully bypassed, or not fully alignment happy fetch unit can cause some serious problems in our performance. Let's stop here for today, and we'll talk about the rest next time.